Hey everybody, welcome back. Time for more fun and adventure in Geodesy. It's good that we are still together, moving right along. We're getting through it. Today we're going to talk about time and different ways that we measure time, why time is important when we're considering position. Now, in plane surveying, really, we have no need to consider time other than like the length of maybe an observation or something like that. But it used to be that in order to determine one's position in terms of latitude and longitude, we had a bit of a problem with time, and we'll go into that. Problems and solutions. So we discussed a little earlier about the fact that latitude, no matter where you are, is quote unquote easy. Easy is always a fun word. Easy to determine. And I'm going to keep referring back to if you're on a ship with no navigation equipment, no technology that we have now. So on a ship, the ship is rocking up and down and back and forth. But if the observer had a way to stabilize a piece of equipment in order to measure the angle, the vertical angle, and therefore the zenith angle between, for example, Polaris or the sun at a certain time of day and the horizon, then he or she could determine what the latitude is. And that's independent of time, provided there's not so many clouds you can't see any of the stars. But you can determine latitude if you have an ephemeris, from any of the star positions, the sun position, and especially easy is the position of Polaris, as we talked about before, because the angle between the observer's horizon and Polaris is equal to the latitude of the observer. So latitude is easy to determine. It's not time dependent. I'll write that down. Latitude is determination of latitude is not, and I'll put necessarily, time dependent. And I say necessarily because, in terms of navigation, even the roughest determination of latitude would suffice for position north and south. Now, in order to determine a position, of course, the observer would need to be able to calculate latitude and longitude, and therefore could figure out one's position, right? So while latitude is easy, longitude has problems. Longitude is problematic. As the Earth rotates, the lines of longitude rotate with the Earth. So if you can determine what the time of day is at Greenwich, England, and what where the sun is or certain stars are during a specific time of day in Greenwich, England, then you can calculate for where the sun is at your position versus Greenwich and use that information then to calculate a longitude. But you need to know time. You need to know what time it is where you are, and what time it would be in Greenwich, England, and that so you can compare those declinations and Greenwich hour angles. So longitude, determination of longitude using observational equipment, non-technical, no satellites or anything. So determination of longitude is time dependent. Bullet point, bullet point. So let's take a look real quick at the spherical Earth model just for a basis of understanding. We have this Earth, and not the best Earth, and we have these lines of longitude in whatever degrees we want to give, right? So let's determine how many degrees of longitude. So the question is, how many degrees of longitude are, and for lack of a better word, I'll say experienced or observed in 1 hour. So remember, the Earth is rotating counterclockwise, and in 24 hours, how far does the Earth rotate? Well, it rotates through 360 degrees, right? So it rotates 360 degrees per 24 hours. So in 1 hour, that would be 15 degrees per hour. So 15 degrees per hour. So if a person can determine, given the velocity of the Earth, where what their solar time is, what time it is in their position by where the sun is, versus what time it is in Greenwich, England, and of course we're not considering time zones. Time zones are a construct that we've imposed onto the Earth in order to make things more convenient. But time is really different. Even if you move 10 feet to the east or west, you're going to have slightly different, although it's negligible, but any amount you move east or west is going to place the sun in a different position from your perspective, which can be measured. So if we're 30 degrees west of Greenwich, England, then we've moved through 2 hours. We're 2 hours time different from Greenwich, England, because there's 15 degrees per hour, right? So 1 hour equals 15 degrees. Okay, so let's step back in history, back to colonial times and expansion and all that good stuff. Of course, in the 1400s through the 1700s, the world community was going through a lot of exploration. We were discovering different parts of the Earth, trying to expand on our knowledge of North America. So a lot of sea travel, a lot of merchant navigation. So a lot of merchant. I'm gonna say mariner, not merchant. So mariner activity. heightened during exploration and expansion. And there's a lot of horror stories written throughout history about ships that were lost at sea because they couldn't determine their longitude. Since longitude is based on time, there would need to be a clock on the ship that would keep the time in Greenwich, England. So, clocks, if I had a clock, minute hand, hour hand, and there's a bunch of numbers around the clock. All clocks through most of the exploration period were pendulum based, or somehow used a gear or something that was subject to gravitational changes. So changes in acceleration and remember, acceleration is a vector, so that change in the acceleration could be the change in the direction of acceleration. On ships, rendered contemporary clocks unusable. And why is that? Well, on a ship, like we said, it's, balancing forward and backward and side to side. It's rocking all directions. It's spinning. All of that movement creates an acceleration vector that counters gravity in some way. So it throws the pendulum off. Directional, I'm going to write it in red, accelerations, or I'll say acceleration changes at sea were a problem for gravity and scoot up. Dependent devices. So ships had a really hard time getting their position. Even being off by a few minutes could place their longitude calculations off by several degrees, or hundreds of miles. So they would miss their target. If you can't calculate your longitude, you also cannot calculate your convergence, so you can't correct your course. So yeah, that's a problem. So 1714. One of the big players in the expansion era and the empirical era, I should say, also was Britain, Great Britain. They were sending ships, and ships loaded with expensive materials, goods for both sale and purchase, were being lost at sea and costing merchants millions, hundreds of millions of pounds, even in that day, as well as lives. I mean, there were Navy soldiers, explorers, captains who were very adept in their fields, therefore very valuable in the exploration era, that were lost at sea and never seen again. So Britain had a real problem. They couldn't predict or forecast the success of their trade routes or their conquest routes, which was really important for the time. I mean, Of course, now we would find that the conquest part a bit shameful, but that was the name of the game in the 15, 16, 1700s. So the monarch at the time, Queen Anne. Oops, two N's and an E. Anne with an E. I don't know if anybody watches that or reads those books or anything, but Queen Anne issued a declaration offering £20,000 to anyone who could solve the longitude problem. And to be honest, I have no idea what £20,000 is right now. I mean, I know it's a lot. It's if we were to convert £20,000 to today's money, more money than I have, or probably will ever have in my life. So that's a lot of money. So £20,000 to anyone who could solve the longitude problem. And this created quite a stir. The world's leading mathematicians and physicists, including Isaac Newton, were scrambling to solve this problem, but they could not solve the problem of time. All of them knew that without being able to maintain a reliable and consistent account or metric of time, that there would be no way to calculate the longitude. It was just that simple. They tried using the moon in its different phases on different dates. That didn't work. And so a clockmaker, sometime after 1714, I don't know what year he presented his solution, but John Harrison, who was a clockmaker. I mean, imagine being a clockmaker and you're trying to solve a problem that people of Sir Isaac Newton's ilk are working on. But John Harrison understood well the mechanics of the pendulum clock, and knew that if he could create a chronometer, if he could create a chronometer that could withstand the movement and atmospheric conditions scoot this up. So John Harrison, if he could create a chronometer or a chronometer, that could withstand, a chronometer is just a fancy word for a timekeeping device, that could withstand the movement and atmospheric conditions experienced by a ship at sea then the problem of longitude would be solved. So he got to it. He wanted to create a clock that could maintain accuracy as much as possible and withstand the changing acceleration vectors at sea, and also be resistant to atmospheric conditions such as humidity, temperature. Then he will have solved the longitude problem. The issue was that nobody had done that before. The only timekeeping devices were gravity dependent, or used pendulums, and what are the weights that are called that you see in a grandfather clock? The weights are dependent on gravity. Those can't swing. So he explored using springs, gears, and atmosphere resistant materials. One of the materials that he recognized right away would be useful is wood. Wood has minimal expansion and contraction with minute changes in humidity and temperature. So he started exploring with wood. He implemented springs and gears and came up with just what he was looking for, Harrison's chronometer. And there's some really good books, some great stories about the highly competitive movement to discover a device that would keep time at sea. Chronometer, which, by the way, so the Harrison's chronometer was resistant to changes in acceleration vectors such as gravity. And he did this with gears and springs, and he used wood in his first models, and then discovered metals that had the this is killing me. I'm not sure if resistant is ANT or ENT. And these things are important, so I looked it up. It's ANT. I was right. Also resistant to changes in humidity and temperature. So the problem of longitude was solved, and it greatly enhanced the economies of the world, exploration, conquest, development. All of these, ships could, more ships could reliably reach their destinations. So colonization flourished. It had a big, big impact. Oh, and by the way, I'll just in a different color. Gave rise to. That's why we have wristwatches. We wouldn't have wristwatches if this problem wasn't solved. Early on, it was pocket watches. So the mastering time metrics is what solved the problem of longitude. So how do we measure time? Now that we have the problems tackled with keeping accurate time, how do we measure time? So, come on, change color. Well, we measure it just like we measure distance. We impose a metric being a unit by which we glean measurements. So something that's 10 feet is also, 120 inches. We can convert to metric, we can convert to chains, whatever. So creating a metric that was stable to measure time was important too. And in fact, it still is. So, what we're used to is solar time. And I'm going to talk about I'm going to talk about things archaically. I'm going to talk about the sun moving around the earth, but we all know that doesn't happen for real. But I'm going to talk about it in those terms. So, the time for the sun to move around the earth entirely, that is, for it to get from one position around the earth and back to its position, is 24 hours, which equals one solar day. And we all know that there are 365 point, I believe, 24. There's about a quarter of a day left over, days in a year. But solar days are easy to calculate because, as long as you have, as long as you can measure a shadow and know your latitude, then you can pretty easily tell what time of day it is. So, solar days, let's see, solar time is easy to observe and implement. However, solar days have a problem. Solar days, or the length of solar days, are not uniform throughout the year. And I'm not talking about daylight. That actual 24-hour period fluctuates given where the Earth is on its elliptical orbit. So let's see. So solar days are not uniform throughout the year. And that's because if, here's the Earth and here's the sun, and the Earth moves, the orbit is elliptical, isn't it? So the movement of the Earth from the elongated axes to the shorter axes creates a change in the amount of time that that one experiences in a day, from day to day. So to combat this, we came up with universal time. And universal time is based on an atomic clock. I believe it's in Paris, but I'm not positive of that. So universal time based on the atomic clock, and our current model of universal time is called UT1. So, being An atomic clock, which is based on a rate of decay and radiation, it's very uniform. So it's uniform throughout the year. Universal time is uniform throughout the year. And for that reason, most of our ephemerides, that is one time metric that's reported on almanacs and ephemerides, because it doesn't fluctuate from one day to the next like the solar day does. So since we are most used to working with solar days, it'd be useful to come up with a method by which we can go back and forth between universal time and solar time. So we have what's called equation time. Which is really complicated, but I'm going to write it out. Let's see. It is solar time minus universal time. Really complicated equation there. So if it's 5 o'clock one day and the universal time is 5 o'clock 0 minutes and 1.5 seconds, then the equation time would be negative 1.5 seconds, I guess it would be. And then you would apply that to you can apply that difference to get back to solar time at any point during the day. So that's equation time. So as I set up there, UT1, that's a 1, is the principal form of universal time. That's our accepted standard. And it has advantages. It's corrected for polar motion, precession, which we talked about before, Earth's wobble on the axis, velocity variations. Really complicated stuff. I mean, I wouldn't mind hanging out and having a beer with one of these guys that maintains and calculates universal time in the atomic clock. Yep, I'm a dork. Okay. So universal time is what is used for solar and stellar or star-based observations. And so we said that we have universal time, and then our accepted standard is UT1. So how do we go from, oh, wrong color. How do we go from this universal time to the UT1 that's corrected? Well, there are resources for looking up the difference. So UT1 is equal to the universal time plus the difference from corrections in UT. And that's often abbreviated. You'll actually see this DUT, difference in universal time. And you'll see that in different resources, charts and things. So, yeah. Moving on, time is getting short. Okay, so that's universal time in a nutshell. And all of this all of this information we're discussing in regards to time metrics is just a broad overview. So that you at least have some exposure to understand what kinds of time are being reported in different situations. So we also have, particularly for astronomic uses, we have sidereal time. Let me rewrite that so that you can see what I'm writing, because you're taking notes and trying to write this down. So I will be courteous and try to make my writing readable. Sidereal, like sidereal. Sidereal is how that's pronounced. Time. And sidereal time is based on the stars. And it's hard to imagine, but if the sun and stars are observed or perceived as moving around the Earth, then the sun, we can say, moves around the Earth in 24 hours, no matter where you are on the Earth. It's 24 hours from one point in a day to that same point in the next day. The stars, that's also true, but we don't really see any sort of ellipsoidal components when we're considering our observation of the stars. We're not considering, I mean, in astronomy we do, but for determining time, we really don't experience that elliptical orbit around the sun as much. So the sidereal time actually comes in at a different metric than a solar day. So let's see, I'm going to write time is relative to the stars. So in a solar day, time is relative to the sun. In a sidereal day, sidereal time is relative to the stars. And you would think that that would be the same because the Earth is just turning on its axis, but it's actually slightly different. I don't know, that creates kind of a short circuit in my brain, but so one sidereal day is the amount of time it takes for any particular star, a particular star, to experience, to return to its same position the next day. So to go from 0 degrees GHA to 360 degrees GHA. 360 degrees GHA. So how long is that? So one solar day equals 24 hours, 0 minutes, and 0 seconds. One sidereal day, I'm just going to say I'll spell it out, is slightly shorter. It is 23 hours, 56 minutes, and 04.1 seconds. So almost 4 minutes of difference between a solar day and a sidereal day. See another comparison. So that's about a change of about 4 minutes. About. Another cool metric is how does that accumulate over a year? So there are 365.2422 solar days per year. But there are 366.242 sidereal days per year. So if we were more used to, if we actually use sidereal days as our time, we would get an extra day every year. I know it doesn't work out that way because it's just a metric, but almost a full day, or a little over a full day, really, by a fraction of a day. So there's quite a difference. So that's about one extra day. There's quite a difference in the length of time in solar days versus sidereal days. And again, the advantage of sidereal days, they're consistent and uniform. Throughout year. So definitely an advantage. And let's see, there's one more day for us to talk about, or one more time metric for us to talk about. We've also come up with, and it's become increasingly important since the advent of the information age, wherein computers are super important. And so the popularity, ubiquity, and democratization of the Julian day has increased since the advent of computers. Julian day, or Julian time. And it's a little bit different than how we think about solar days and sidereal days. Solar days and sidereal days are about measuring cycles. How many times, or how long does it take for the sun to return to the same place the next day? How many hours does it take for for this particular star to return to the same spot? So it's all cyclical, and so errors that are not predicted or managed can accumulate over time. The Julian day is continuous. So we don't have a 5 o'clock a.m. and a 5 o'clock p.m. Julian day, or Julian time on one day, and then the next day we also have a 5 o'clock, and it's continuous. And it is actually the number of days, and these are sidereal days. I'm sorry, no, they're the solar days. No, sidereal. I always forget that. The number of sidereal days and decimal representations of partial days. So in decimal representations, since noon, and again, that's sidereal time, on January 1st, I think it's 4713? Yep, BCE. Why so long ago? Why almost 5,000 years ago? Well, the reason is because much like we impose positive numbers on our coordinate systems, well, by choosing a date so far back in archaic history, we don't ever have to consider history with a negative Julian time. Excuse me. Apparently, it makes the mathematics easier. I don't know why, but computer dudes like Julian time. So again, this is based on sidereal days, is my understanding. Let's see. Oh, and that was in Greenwich, England. So January 1st, 4713 BCE. In Greenwich, England. So you come to find out, in terms of navigation and cartography, time, all these metrics that we are so dependent on are attached to Greenwich, England. I'm sure that's a fascinating history, but I haven't delved really into why Greenwich. I know it was the seat of power during much of the Renaissance and the discovery period thereafter. So that's Julian time. And just to pull some numbers out of my head, I have no idea what the Julian date is right now, but you might see something like 2422287.462. So that would be, the integer part, the 2422287 is the number of days since the Julian year, and then 0.462 means that we're almost halfway through the day, so that would be almost noonish. So days are broken up into decimal parts rather than hours and minutes and seconds. Makes the math a lot easier. Kind of like working with radians. And I think that's about it. Shorter lecture today. This is just kind of some leftover stuff that I wanted to just touch on. Just kind of, here it is. Here's a cartoon for you to see regarding time and metrics. But you will see these representations of time again and again. Throughout your careers. They are, and it's important to know the difference. So that's it. I think I'm going to wrap this one up. And if you have any questions, we're going to get back to some of the mathematical model stuff, the spherical stuff tomorrow. And we're going to start looking at convergence in a more detailed way. So hold on to your hats, brace yourselves, and we'll see you next time.